A single-layer perceptron is a type of supervised artificial neural network with no hidden layers that can perform linearly separable classification. In simpler words, if we look at this figure, we can see that the neuron, or the fundamental unit that processes our input, applies some weight and then passes it directly to the output. In a multi-layer perceptron, there would additionally be a loss function in more than one hidden layers between the input and the output, and a much more complex activation function than just a simple summation of the weights as we see here before the output is created. To explain the structure of a single layer perceptron in a much better way, I have prepared this workflow where we first begin with the input layer, where the perceptron can take multiple input signals. Then, depending on its weights, which are randomly assigned with the Python package that we are using, which is sklearn, these are associated with the inputs and they basically signify the importance of our input. Normally, before we even receive the input at this stage, we would have standardized it, but more about that later. Then we go on to the summation. The perceptron computes a weighted sum of the inputs before it forwards it to the activation. The activation function in the case of a single layer perceptron is a simple decision maker, which essentially is often a step function. So based on the sign of your summation, it decides what class label to apply. The output is itself the label that is associated with the decision that we made at the step 4. We want to have convergence towards certain accuracy. What I mean by that is that when we gradually allow the weights to be adjusted with each iteration, depending on our learning rate, which is normally set to 0.001, we can reduce the error in our accuracy over each subsequent iteration. So for the algorithm, I will basically be showing first the algorithm implementation on a standard dataset, that is the iris, flower and petal dataset. And then I will show an example that I have created from a customized UniProt data. More about that later. The basic steps of the algorithm that we will apply are first to import the sklearn libraries, some numpy module, then some functions that will load and pre-process the input data. Then third, to train the single layer perceptron, and then finally simply evaluate the model using an accuracy printing. In order to pre-process our data before it is sent to the perceptron, we need to standardize it. In other words, we will normalize our input values to have a mean of 0 and a standard deviation of 1. This is important for the convergence of any machine learning algorithm where we basically want our inputs to affect the result equally. Essentially, this is going to help the each and every feature of our input to affect the decision making function. With each iteration of the single layer perceptron, the weights will be adjusted automatically. Finally, the evaluation of those decisions will be a simple accuracy calculation, which is the number of true positives divided by the total number of positives and negatives. And this is the basic test that we are going to calculate. So to begin, I will first discuss the perceptron model that we develop on the iris dataset. We begin with importing the NumPy package, which will be important for some manipulation of dataset down below, some sklearn packages. The load iris module already contains the functions that can help us access the iris dataset. The model selection package contains the train test split It essentially helps us to split our data set in any fraction that we specify. We can also include some standard scalarization function and the accuracy score function from the sklearn package. And most importantly, we have the perceptron model, which we are going to import from the sklearn.linear model library. To load the iris dataset, we simply call the load iris function. We can assign x as our training features and the y as the training labels. Essentially, these are unique labels: setosa, versicolor, virginica, and the x features are sepal length, width, and petal length and width. One thing to note here is that all of the data that we are working with right now is numerical. As we go below, for ease of our calculations, we are only taking a binary classification model here. So we are going to remove the test features or the features which lead to anything other than 0 or 1 label. As we move forward towards the train, test, and split, we can modify the test size to any value that we like. Here, for example, we can set to either 70% train test or 90% train test. It really is up to you, as it's an arbitrary choice. The random state only acts as a seed for your random calculation. So if you do the steps in your system exactly as I do right now, you will receive very similar or actually identical results. If you change the random state value, then the values that you receive will also likely be different. Once we have created our train test split dataset, we can normalize all our numerical features as well as our target values. Then we can call the perceptron model with the number of iterations. That is also a parameter that is up to us to set. Normally, setting it as 1000 is considered standard. The learning rate and the random state is also provided here. Then we can simply fit this perceptron model against our training dataset and our training features dataset and our training labels. Once the perceptron model shows you correctly created like this in our Jupyter notebook, we can go ahead and predict our X test dataset that was previously created in the train test split function. The predictions that come from here can be input directly in the accuracy score function. That is the that is the function fetched from the sklearn package. And here the accuracy, I'm currently displaying it with only 2 decimal points, which is a personal choice, but also just sufficient for us to see the final answer. The value that you see here will completely depend on what kind of model we choose or the number of iterations you provide. Since this dataset is quite simple to use, it's fairly reproducible even if you change a different parameter in the number of iterations or the learning rate. Now, if we move towards our customized dataset, where I have some categorical labels, which basically means I have textual values in my dataset, I would have to convert those values into a numerical format before I can go forward with the standardization steps or even train my perceptron. So first, I begin by loading my TSV file, protein sequences, which have certain numerical features and some textual features. To make my life easy, I only take the length, mass, and the enzyme catalog number as the actual features for this dataset. I'm going to predict whether the sequence belongs to Homo sapiens or not, depending on these features. The entry label that you see here is just for your reference. I do not use it actually in my dataset. So as part of my data pre-processing, or basically cleaning, I'm going to assign the label 1 to any of the records that do not contain Homo sapiens, and to all the records that do contain Homo sapiens, I'm going to label them as 0. Do note that I'm currently assigning everything in a textual format, and this is intentional because if you don't put the string values over here, then the second time that you run the str contains function, it will give you an error. So once you have completed your string filtration, then you can cast the entire column as integer. Moving forward, I'm going to separate the enzyme catalog number into more individual classes. For your information, the enzyme catalog number is composed of 4 different domains of information regarding the enzyme, and these I have roughly classified as reaction type, enzyme subclass 1, subclass 2, and then the enzyme identity. More information about this can also be searched on the internet. But for our use case, these numbers are fairly important because they are going to act as individual features. One thing that I have done additionally over here is that I have removed any of the bad or erroneous texts that are available inside these individual categories of enzyme catalog number. So this is actually an artifact of the entry. Whoever created these entries may have forgotten to clean them, or these numbers mean something that are not necessarily important for us right now because we only want integer values. So I'm going to clean away all of those non-integer values. Finally, after all my data frame is prepared with the numerical values, I'm going to go ahead and typecast it to numeric values so that I have an in so that I can move forward with the standardization process. Now, like we did before, we are going to split our datasets between the features and the label category. So the X variable here takes all the features, and the Y variable takes the organism, which is our final category. Then we can train and test split as we did before. Here I'm also going to test a different test size. But the rest of the process is fairly straightforward, where we fit the perceptron model, we go ahead and predict, and as you can see, the accuracy of our model is already quite high. We can also try to modify certain other parameters and see if that also helps our model get even better. But for a first test case, this accuracy is quite optimistic, which also gives me an indication that the hypothesis that I began with, which was that the features of enzyme category, the length and the mass of the reference sequences is sufficient for categorizing an organism, was indeed correct. And this model was a good binary classifier for that use case. One of the disadvantages that would be important to discuss at this point regarding single layer perceptron is that it is a simple binary classifier. So there is no scope of back propagation or basically iterative improvement of the model. It is too simple for its own good. So if there are some non-linear relationships between our data set, we will not be able to capture it. Here, it basically is a simple linear calculation between all of our given features. It is possible that if I test my same data set with a non-linear relationship, I could even make a better accuracy with the multi-layer perceptron model. Uh, yeah. So I hope that you can also go ahead and experiment with some more of your bioinformatic data sets, as this kind of model preparation can help you to reach a higher amount of accuracy with the more complexity you provide to it. Thank you.